So we looked at previously the discrete charge case where we had a cluster of individual charges and we asked what was the effect of those charges from the source to the field point. But now let's look at the section 2.1.4 that looks at the continuous charge distribution and see how we modify the electric field equation. Suppose, let's take for as an example, a line charge. Suppose we had charges that were along this straight line. I mean, it does not have to be a straight line, by the way. Sometimes we get fixated with straight lines. So I'll just make it any arbitrary line. As long as it's a line and all the charges are on it, meaning it's a one-dimensional case. And we take this to be our source charges. And we ask again the question, what is the effect of this source charges in the field point? Let's take the field point to be some distance away, let's say at this point. So we ask, what is the electric field contributed by all the charges along this line? Right? We ask that question mark. Well, let's make some assumptions first. Let's assume that the charges are equally distributed throughout the line. In other words, if I take any segment of the wire and look inside there, I will find some charge, let's call it dq, occupying the space. And the length of the wire, if it's L, then the length, the space that it occupies will be some dl. And I'll make it dl prime, just to remind us about our prime notations and unprime. Wherever we find the sources, we will indicate that space as prime space. And whenever we are in the field, we will unprime the variables. So we'll ask the question, since it's evenly distributed, so let's say it's uniformly charged, uniform charge distribution. That's what I'm trying to say. Now, since if I go to any other location along the wire and I look at the amount of charge in there, dq, and the space it occupies, some dl prime, when I take the ratio of dq over dl, I should get the same value. Okay? So we say the charge density. There is a charge density or a line charge density given by this formula. To make the analogy, just think of a drop of water with a bucket of water. Right? The density of a drop of water, if it's 1, then when we know that the density of a bucket of water will also be 1. However, the magnitude, the mass of this bucket of water is much bigger than this one, and the volume occupied here is much bigger. However, the ratio of mass over volume, or big mass over big V, will still give us a value of 1. Right? So because here we have a mass density, mass volume density, where we have a uniform mass distribution throughout the molecule of water, or the bucket of water. The same analogy goes here for the charge distribution. So we'll use lambda instead as our symbol for the line charge density. And when I cross multiply here, when I isolate the dq, I will get lambda times dl prime. Okay? And let me just write that quantity over here. Lambda is equal to, dq is equal to lambda dl prime. Right? And now, since I'm asking what is the contribution, let's say, of this charge to that point, well, this little charge will say my contribution along this line to that charge is some dE. I'm contributing an element of dE. Let's call this subscript dE1, pointing in that direction at a distance of R1. This guy here also contributes to the electric field at that point, pointing in that direction, dE2, etc. Right? So everybody will contribute. And again, the game is, because of the principle of superposition, we can sum up all the little contributions of charges to the electric field there. to give us the total. However, since we're talking about infinitesimal, and the charges are everywhere occupying space along the wire, we have to use the language of calculus. It's no longer discrete, but I'll just modify this now, so that now the electric field will be equal to 1 over 4 pi epsilon 0, the integral, which is also a summation, and the Q, I'm summing over the small elements of charge, dq, and here I have my 1 over r squared, pointing in the radial direction, r hat. Okay? So this is how we modify that equation when we're dealing with charge distributions. And when we're dealing with discrete charges, we will use this equation. So let's call this equation number 6. Yep. Here I am playing with a one-dimensional case. We can extend the same idea to a two-dimensional and three-dimensional case. So let's look at the two-dimensional case. Right? Suppose I have a lamina, a piece of paper, for example, is a lamina, a plane where all the charges are evenly distributed around it, inside of it. Right? So here's my plane, and it does not have to be straight squares and rectangles, it can be curvy. Right? So all the charges are here, and they're evenly distributed throughout. And we ask the question again, if I have a surface area of charges, what is the contribution of these charges to a field, to a point in the field, let's say that point? You know that every single part of this lamina, the charges residing there will contribute to the field there, right? And again, we just modify here because the charges are evenly distributed. If I look at any little space in here where a charge is residing, some dq, it will occupy an area that is represented by some dA, right? If the total area is A, then the small infinitesimal area that we're talking about is dA. Again, we have to use the charge density method to actually get rid of our dq. Here we use sigma, which is the surface charge density. Right? And surface charge density sigma is given by dq over dA, charge per unit area, right? And again, this quantity will be constant. So when I cross multiply, I get dq is equal to sigma dA. It's constant if we have a uniform charge distribution. If it's not a uniform charge distribution, we cannot claim sigma to be constant. However, there is still a surface charge density, which will be dependent on other variables. Right? So in this case then, for this two-dimensional case, I have dq will be replaced by this quantity here. Okay? So here dq will be equal to sigma dA prime. Right? And in each case, I can replace the dq with this quantity. So this dq will be now lambda dL, and here it will be sigma dA. And the same thing goes for the three-dimensional case, where we will have for 3D. In the three-dimensional case, which is more realistic in the real world. If I charge this marker completely, the charges will reside everywhere in a three-dimensional space, right? So in that case then, the charges occupy volume, right? And let's say we have charges all over the place, evenly distributed. So and again we ask, what is your contribution to the electric field at some distance away at the field point? Again, each of them, if you look at the charge here, it occupies a volume space, and this dq, the volume, normally we should write it as dV. However, because in electromagnetic theory, we're going to reserve V. We have a special meaning for it in electrostatics and in this course. So we're going to avoid using V. V is for potential difference, for potential, we use that. So to avoid it, this textbook you're using uses the Greek letter tau. D tau will represent our element of volume. And again, I will put a prime there to indicate that I am at the source. I'm dealing with the charges that occupy a volume space here at the source. So again, if we work it out, we'll see that in this case, we'll use rho to represent the volume charge density. And rho will be charge per unit volume, d tau. Again, dq in this case will then be sigma d tau prime, okay, for the volume. And again, this is the quantity that I will replace here for the dq in my equation number 6. Equation number 6 is the only equation we have. This is Coulomb's law for continuous charge distribution. This is Coulomb's law for discrete charge distributions, right? Okay, that is our starting point then. In terms of, next what we will do is look at exercises, practice problem, so that we see how we actually go about solving problems using these equations.